This meeting is being recorded.
Section 9.7 introduces us to hydration of alkynes. So we can compare this to hydration reactions of alkenes that we looked at in chapter 8. So they have this acid catalyzed Markovnikov hydration. So if you remember, that would be H and OH addition with the OH in the more highly substituted spot, and H will go where H is. So this is generally catalyzed with mercuric sulfate, shown here, HgSO4. Because this is a fairly slow reaction, because we need to form a vanillic carbocation intermediate in this process. So because of that, we generally don't see just aqueous acid conditions, so H2SO4, H2O on top of the arrow, but we also see this HgSO4. So what happens is we have our alkyne, our reagents are added, and we form an enol, which cannot be isolated. It quickly changes, it quickly tautomerizes to form a ketone product. So let's take a look at these steps in just another broad overview here. So we have our mercurinium ion formation from this mercuric ion here. So the triple bond attacks the mercury cation, and we end up creating this here, this mercurinium ion. So this is our mercurinium ion. And then that is attacked by water, and we see this lone pair here attacks this carbocation that has formed, and what happens is we add water to our double bond, and then last step here we have deprotonation. So this water molecule will grab that proton, and we have this temporary product that forms, and we'll take this one step further on this slide here. So we'll start with what we ended with before down here. So we see this process where our enol intermediate is formed when a proton, so the double bond then grabs this proton here. We have some movement of those electrons in that bond, so we create water here in this first step that we see below. And then in this step here, we see our rearrangement of our molecule, and then eventually, as we mentioned, a proton, so hydrogen, has replaced the Hg2+, so that's what we see here, this leaving group. This Hg2+ has been removed, and we finally have our enol intermediate at this step. So then the next step involves a proton transfer. Right, so this step here with our enol, the pi bond of the enol is protonated, and we have this resonance stabilized intermediate that forms. And once that happens, we have another proton transfer that grabs a proton from this resonance stable intermediate form over here, and then our ketone product is formed. So this is called a process of tautomerization. This keto-enol tautomerization is what happens when we have this hydration of alkynes in aqueous acidic conditions. So we go again from an enol to a ketone, and generally the equilibrium will favor the ketone product. So another type of hydration reaction is the hydroboration oxidation of alkynes. This follows the same process as alkenes, and we'll see that we have radioselectivity of anti-Markovnikov addition now. So we have some peroxide, and we also have basic conditions now. So we'll see this tautomerization again, just like we saw with the acidic conditions, but now it's base catalyzed. So let's see what that looks like. How is that different? So we have our same process here, right? We have our starting alkyne. We give it these conditions here of hydroboration, oxidation, and we see our enol that has formed, right? So this is the this is our aldehyde product that will form. So that's one difference that we'll see. But this is our enol intermediate here. So we'll start at this point on this slide here. The hydroxyl group of the enol is going to be deprotonated. So we have our basic conditions. We grab this proton, we move some electrons, and we get this enolate ion that forms in basic conditions. So we didn't see this before. And we have this enolate, which then is protonated, right? We have this other form here with this lone pair. This will grab a proton over here, and we will regenerate that hydroxide ion. And what happens is, once we protonate this enolate ion, we'll end up with an aldehyde as our final product. So when we have basic conditions, the enolate ion is a difference, and then our final product is no longer a ketone. So let's take a look at what if we only wanted to have a single addition, right? We wanted to prevent a second addition. We could use, instead of BH3, instead of borane, we could use a dialkyl borane. So two of those hydrogens have been replaced. As we see, we have one listed over here, right? So these two alkyl groups are in place of a hydrogen, and then these are the two alkyl groups in this bicyclo structure over here. But both of these have bulky alkyl groups, which prevent a second addition due to steric hindrance. So they block that second addition. So that'll prevent undesired products. So in this case here, say we wanted to, we use this modified borane reagent, right, that cyanoborane listed in step 1 here, to prevent multiple additions, and then we would have this aldehyde product that we could control. So we use modified reagents at times when we want to control reactions. And we can also control regiochemistry. So say we want to follow Markovnikov addition, Markovnikov hydration of a terminal alkyne, we can produce that ketone. So again, that would be that top pathway here. We have our aqueous acid, mercuric sulfate. We end up with our product here, a methyl ketone. Then if we follow the path down here with the hydroboration oxidation, and say we want to control our product, we can use that dialkyl borane instead, but we have basic conditions now, so we create an aldehyde product with the anti-Markovnikov hydration. So that's everything from this section. We'll continue with section 9.8 next time.